as follows from the title. Today I'll be talking about microfabrication. And the background picture here is what an artificial intelligence thinks about my title. So I uploaded it into the neural network, and this was the result. It's not very precise, but hopefully explains a few things about things we're working at. In Oldenburg, you've got a nozzle. We do additive manufacturing, which is 3D printing. And we're actually working most of the time by fabricating metal structures. So this is all kind of reflected here. Anyway, so 3D printing is a family of very different technologies that actually grow in popularity more and more for a number of different reasons. Two of which are relevant to the topic of my talk today is the possibility to basically choose almost any design you want. So you make a design in your CAD file, and then you load it into your printer, and then the machine is doing the rest. It's fabricating the object. And the second reason is the possibility to do rapid prototyping. So obviously, you can do 3D printing at very different length scales. You can fabricate large objects like buildings. You can make not so large objects, so the scale of centimeters. But you can also go into a realm of micrometer and nanoscale dimensions. And obviously, this has a lot of interest because these advantages that I mentioned before actually manifest themselves even stronger at micro and nanoscale. Why? Well, first of all, is a design freedom and the possibility to fabricate a structure in a single step. Typical microfabrication is a multi-step protocol that can take many steps. In microfabrication, depends what you do, but it's sometimes very difficult to do prototyping. If you work in a company like Intel, it can take you 3 years between the time you submit your design and the time you get your microchips. So this is a lengthy process. And in traditional microfabrication, you can't really fabricate the structures with high aspect ratio. You can fabricate three-dimensional objects. You have to be creative. But if you need very high aspect ratios, it becomes very complicated. And finally, of course, you can make truly complex designs which are difficult to achieve by whatever post-processing. So if in a traditional manufacturing, I can fabricate two objects and just glue them or stitch them together somehow, you can't really do this in a micro and nanoscale. All right, so what kind of technologies already exist for making things with these dimensions? So here I pulled a few examples of objects that are fabricated by commercial instruments, which are based on a two-photon polymerization techniques. And here you can appreciate yourself the level of detail, the resolution, and the complexity of things you can fabricate. So you can make replicas of famous objects at the micro scale. You can make fancy mechanical materials. You can make really complex structures like this knot with the extra nanostructure. You can make patterns, whatever you like. However, if you want to do any real-world application, most of the time you want to have the possibility to manipulate electrical signals. So if you want to have a new biosensor or any kind of electrochemical sensor, if you want to have an electrode that you're going to implant into a mouse brain, if you want to make an integrated circuit, you need the possibility to manipulate conductive materials. And here, basically, you're sort of stuck with the photopolymerizable resins, which most of them are actually insulators. So it works really well, but it's really difficult to use it for real applications where you need conductive structures. So in electrochemistry, we actually quite naturally overcome this limitation. So by definition, we work with electrical conductors. We work with a variety of different materials, metals, particles, semiconductors, and so on. So we have seen today also some examples. The challenge, however, is to really integrate these advantages and to make our electrochemical techniques tools to achieve these complex multi-material designs. So this is the challenge that we tackle in my group in Oldenburg, and we fabricate a variety of different materials. Most of them are metals. So here, these are, again, electron microscope images, and they are false colored, just to have a little bit of artistic representation. But you can see that we are now capable to process structures made of copper, silver, iron, gold, platinum, nickel, cobalt, manganese, tin, and so on. How do we do that? Well, basically, we take advantage of a very simple process as electrodeposition, but we do it in a confined environment. What does that mean? It means that we have a nozzle that we position close enough from the conductive substrate, and we basically just shower this conductive substrate with the precursor ions. And then the electrodeposition is basically supposed to happen only in this confined space between the nozzle and the surface. You can also do it, so this is something you can do in liquid, so basically like in a traditional electrochemistry way. You can also work with this scanning droplet cell configuration. Probably some of you know SCCM. And basically here you simply limit the electrochemistry to the footprint of this liquid meniscus between your nozzle and the surface. So you can do this in a variety of different configurations. I will talk about a few of them today. So let's start with printing in liquid environments. So for that, you can use a technology that is known as fluid FM. Fluid FM is basically an AFM, so you still have the AFM laser feedback. You have an electrochemical cell where your substrate is a working electrode. You throw some other electrodes in the bath, and you have a cantilever that has a microchannel in it. So this is maybe a little bit better schematic representation. So you actually apply a pressure here. It can be positive or negative overpressure. And because of the microchannel and the aperture here at the pyramidal tip, you can basically manipulate tiny volumes of liquid and deliver this liquid where you want. So this is how this cantilever tips look in electron microscope. So you can see here a typical pyramid, and the opening at this pyramid is about 300 nanometers. Well, there are also other designs. So this is a commercial product, you can buy it. And quite some time ago, Luca Hirt has shown how you can use this technology for 3D printing. So he had the fluid FM cantilever. He was applying an overpressure here. He was showering his conductive substrate with a copper ion solution, and then basically monitoring this deflection signal. So when the metal is growing, the cantilever deflects. You measure the change in the deflection voltage, and then basically when you reach a set point, you just retract this cantilever and you continue the process. So if you do it in a simplest configuration, you can fabricate, well, basically this is just an array of pillars on a surface, which is probably the simplest object you can do. This is a video that demonstrates how this is actually happening. Is this running? So basically, you just go and fabricate it layer by layer. So you print a first layer of a couple of 100 nanometers, then you, well, I don't know, the video doesn't work. Just trust me that you can do it in a layer by layer configuration. You can, of course, fabricate much more complex structures. So here is a demonstration with, again, done with a fluid FM. And this time it consists of many voxels, so three-dimensional elements. I think this was over 100,000 voxels put together. And this forms this, I would say this is already a sub-millimeter structure, but fabricated with a microscale resolution. So again, you can see yourself that using electrochemical techniques, you can use them for fabricating truly very complex structures. However, when you print in liquid, it allows you for a design freedom, but it has actually a limited resolution. Why so? So if we want now to change the resolution of our structures to a true nanoscale, so scale below 100 nanometers, a rather obvious way to do that is to reduce the size of this nozzle. And if you reduce the size of the nozzle, at some point you'll find out that basically the resolution stops improving anymore. Why is that? It's basically because this cartoon is actually very misleading. So you think about 3D printing with this tiny clouds of ions that exist, or better to say flux of ions that exist underneath your print nozzle. But in fact, when the nozzle becomes small because of diffusion, convection, migration, whatever other mass transport you have, this cloud of ions becomes that big. So it's probably going to take the whole screen. How do we know that? Well, we took an advantage of another technique where we used this double barrel capillaries. So one barrel we used for the feedback, so simply to keep the distance between this growing structure and the print nozzle constant. And then the other one was delivering the metal ions. So this is the image of the actual nozzle, which is about 30 nanometers across there. And you can see what kind of structures you can fabricate with this. So this is truly far away from nanoscale dimensions. It's about maybe 600, 800 nanometers in the best case. So if you want to fabricate truly small things, you probably have to consider another approach. So something like this droplet cell configuration. So in this case, you equip your system with so you need to apply a potential to this counter reference electrode in your nozzle. You bias your working electrode, and then basically your job is just to make sure that the tip is retracting together with the growing structure underneath. And that seems to be rather trivial. However, as you start reducing the size of this nozzle, obviously this meniscus becomes smaller and smaller, leaving you much less margin for error, basically. So what can happen is, in one scenario, you simply just, if you try to synchronize the movement of your nozzle with the growing structure, in one case, you just lose the meniscus if you move too fast. If you move too slow, then basically the metal is going to grow inside of your nozzle, and maybe you can use this for some sort of bipolar electrochemistry, as we heard today, but that is not what we wanted. For us, this is basically the end of our printing experiment. And what we found out, again, is that you can still synchronize the movement of the nozzle at a micrometer scale, because the relative deposition rate, so the rate is here in the vertical axis, at the size of hundreds and thousands of nanometers is relatively low. However, as you reduce the size of the nozzle, you will see that even tiniest variations in the nozzle dimensions would lead to drastic changes in the print rate, so you will never manage to synchronize your printing based on the experiment with one nozzle and apply it to another one. So what we did was basically automated the process by breaking it down into individual steps. So the setup remains the same. What we do, we simply approach with our nozzle to the conductive substrate. We measure a current. So obviously when we are in this configuration, there is no current, there is no meniscus. When we land, we start detecting some small current, and we immediately command our nozzle to retract. It goes up, the current drops again, and then it reapproaches and deposits another layer of material. So you basically break down the fabrication process into very tiny, short periods of actual printing. So the existence of this meniscus is only a couple of milliseconds on the surface, so you repeat it many, many times per second for your printing experiment. So using the nozzles with hundreds of nanometers dimensions, we're able to fabricate really easily, reliably, the structures containing thousands of voxels. But also what is crucial here is that you can place these voxels now really next to each other. So here this is these 4 coils that are printed kind of in parallel, and you can see that basically you can achieve dimensions and placing of these voxels that you can't really achieve in liquids. You can fabricate the structures with very high aspect ratio. So these are pillars printed at also at different voltages. And when we use the nozzles, which are really small, so somewhere around 50 nanometers at the opening there, we can also play a little bit with the process conditions. So we can change the voltage or the current that we allow to pass through our system. And then this allows us to also to control the pillar diameter from something like 60, 70 nanometers to over 100. You can take advantage of that, and you can basically, on the fly, almost vary the resolution of your printer by changing, for example, the voltage in this case. So here we printed these pillars in the front row with a variable voltage, and the pillar in the rear were printed with a constant voltage. Here in the inset, you can see that truly the variation of diameter happens in these ones and doesn't really happen in the back row. You can also stack these individual layers with a small lateral shift, so you can fabricate the structures that have a tilt. But also, if you now, instead of breaking the meniscus upwards, you would break the meniscus sidewise, you can fabricate the structures which have these overhangs, and this is the freestanding ET and H logo that we printed with about 100 nanometer dimensions. Then we were asking ourselves, okay, so where is the limit for this? So how far can we take it? So we got these nozzles which are really, really small, having the single-digit nanometer opening. So this is a TM images of a few of them. And sometimes when we bring it to TM, we don't really see an opening. It's just too small. And if you try to go with a higher magnification, it just bursts in the electron beam. So we do the conductance measurements. And from this one in particular, we could infer that this is about 0.9 nanometer opening. That means that at a time, only one metal ion can travel through this nozzle. And then when we started to use these nozzles, we found out that actually the structures that we print are not that small suddenly. And when it's reproducible, we were always limited at around this 25, 26 nanometer mark. And if it is irreproducible, you can go to the scale around 10 nanometers, but it doesn't really work reliably. Anyway, I will skip the reason why this is happening, and I will just quickly jump to what kind of materials we also print. So here we analyzed what kind of microstructure has the structures that we fabricate. So we did the FIB cutting, and we see very little number of defects in this structure. So this black dot is probably like bubbles trapped during the deposition or stuff like that. This, what we fabricate is, again, by definition, is an impurity-free metals. So they are as clean as we can measure them. The other interesting direction that we explore now is the possibility to also basically play with the ion flow. So if you have this double barrel pipette, and now you fill the barrels with different metals, if you apply the voltages in a specific way, you can fill this meniscus with one metal or another. And that allows us to fabricate structures like that. So this is the contrast here in the black and white is two different metals, gold and copper. You can also mix them in a different proportions if you like. That is a little bit more tricky, however. And here I come to my conclusions. So hopefully I was able to convince you today that you can use electrochemistry for 3D printing, and you can use it for fabricating metals in particular with the small dimensions. The current resolution we have is about 25 nanometer for printing in air, on 600 nanometer for printing in liquid. And yeah, this is a little bit like an outlook from my own perspective that the future of this technology is multi-material printing. I would like to acknowledge the team, so the students that participated in this, our collaborators from NTU and from ETH Zurich, of course the funding agencies for sponsoring this research, and I would like to thank you for your kind attention.